So we're going to have a look at section 4H from the syllabus, the GCSE Chemistry syllabus. This is looking at synthetic polymers. We're going to focus particularly on addition polymerization. Before we start, what I'd like you to do is to have a go at listing the pros and cons of plastic. Press pause, and then when you've finished, press play again. So the pros and cons of plastics that I've got. Here we go. Pros of plastics, I've put durable. They last a long time. They're waterproof, so that means that they can be used outside in the rain, in swimming pools. They can be coloured, so they're great for children's toys. They can make you can use them. You can highlight differences in the materials by colour. They're flexible, or they can be flexible. That's very useful. Electrical insulators. That means that they can potentially be used for electrical wires or electrical components. And they're unreactive. That means that they don't react. So that means they last a long time. And that leads on to the cons of plastics. We'll talk more about that later. So, syllabus statements, press pause on the syllabus, on the video, and we'll come back to these. 4.44, we're looking at addition polymerization. So here's a simple representation of addition polymerization. We've got a small box, and that represents our monomer. The idea is we have lots of our monomers all lined up. They're separate at the moment. So we've got 1, 2, 3, 4, 5, plus dot, 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 plus dot, dot, dot. That implies that we've got many more than 5. And when they react, all that happens is we produce one long chain. And that's called the polymer. In terms of properties, with addition polymerization, we've got to start off with a small identical alkene. So we've got one alkene, the same alkene, the same alkene, the same alkene, the same alkene. Because it's one small molecule, it's got weak intermolecular forces of attraction. That means it's going to have a low melting point, which means it's probably going to be a gas. Our polymer, on the other hand, is a much, much, much bigger molecule. It's one large molecule, a long chain of repeating units. There's the units repeating over and over again, held together by covalent bonds. And because it's one big molecule, it's got much stronger intermolecular forces of attraction, which means it's going to be usually a solid. So we've got some examples that the syllabus wants you to know about. Let's have a look at polyethene in the first instance. So remember our monomer. In this case, it's going to be ethene, 2 carbons, eth, and it's got a double bond, which means ene. So here we've got ethene. I happen to have drawn 3, but remember we've got the plus dot dot dot, plus dot dot dot, and that implies that we've got more than 3 ethene molecules here, hundreds of thousands of ethene molecules. And when they react, they produce this. Here is our repeating unit. It's based on 2 carbons here, and then the same 2 carbons, and then the same 2 carbons. There they are repeating. Okay. The bond dot 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 rather than the plus dot 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 implies that the bond goes on and on and on with a similar kind of structure. Same here, bond dot dot dot. The molecule continues. Here it's separate molecules, adding another one, adding another one, adding another one. Here the long chain just continues. There's our repeating unit. Let's have a look at what happens and how it happens. So in this example on the right-hand side, again with ethene, what I've done is I've highlighted one of those 2 carbon-carbon double bonds in red. There, there, and there. And the idea is, when it reacts, that bond flips up, and it flips up some more, and then it flips around, and then at this stage, what happens is, this carbon here only has 3 bonds, this carbon has 4 bonds. This bond is shared between these 2 carbons. Same here, same would happen here, the same would happen here to make our long chain. So it's this molecule here, which is the same as this one here. The hydrogens are bent, but essentially it's the same molecule here. So we've got one of those carbon-carbon double bonds flips up and goes round, and eventually it bonds together to make your long chain. Okay? Have a go yourself at working out the following displayed formula equations for polypropene and polychloroethene. Press pause on the video, rewind perhaps if you need to for that previous example, and have a go at these 2. Okay, here's polypropene. The trick is with polypropene, you've got to draw it like this. You'll get yourself into all sorts of problems, which we'll talk about in a minute later. So here we go. Remember, one of these 2 bonds flips over. One of these 2 bonds flips over. One of these 2 bonds flips over. The same here. So what happens is it produces this. So you've got your 1, 2, 3, 4, 5, 6 carbons. There they are, 1, 2, 3, 4, 5, 6. On the second carbon here, it's got a CH3 group. There it is. Second carbon here, CH3 group. There it is. Second carbon here, CH3 group. There it is. And remember again, we've got the plus dot dot dot, plus dot 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 to imply the molecules go on and on and on. We've got more than one molecule here. Here the molecule carries on. It gets longer and longer and longer. That's polypropene. Polychloroethene. Oh, sorry, my apologies. This is a way not to draw your monomer in this case. Don't use it like that because it can lead you into all sorts of problems. What people start to do is to try and bond to this carbon going along, and it just doesn't make sense. You end up having carbons having too many bonds. So if you made that mistake, draw it always like this. Let's have a go with polychloroethene. I've done it the other way around. This is polychloroethene, and we've got to work out the monomer from this one. So my repeating unit is here. My repeating unit is here, is here. So what we need to do is pull this back up here and have this arrangement, but with a double bond here. You should see 1, 2 carbons, 1, 2 carbons, the chlorine up here, 1, 2 carbons of the chlorine up here, 1, 2 carbons of the chlorine up here, 1, 2 carbons of the chlorine up here. And this is polychloroethene, this must be chloroethene. Or more polytetrafluoroethene. Tetra means 4, so we've got ethene with 4 fluorine atoms instead of the hydrogens. Again, press pause, see how you get on. There's tetrafluoroethene, and again, when we react, it produces this. What I've tried to show you is a very simplified version of what's going on here. So you must always start, when you're doing addition polymerization, always start with this arrangement. You can draw your alkene in all sorts of different ways. This is by far and away the best way to start. If you do have this, then when you have more than one reacting, all that happens is you produce this. These could be hydrogens, these could be methyl groups, ethyl groups, chlorines, bromines, alcohol groups, doesn't matter. But whatever you've got up here, WX, 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 we've got the same here, YZ, 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 same here. So that's the technique for working out the way that addition polymerization works. Another way of writing it is to say, rather than 3 plus dot 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 plus dot dot, we've got n lots of this, where n is a big number. And when it reacts, it produces this as a repeating unit. So we've got brackets as it works in maths, and then we've got n lots of whatever's in that bracket. So these two are equivalent. This is a quicker way of showing it. And this may well be a way that you want to do because it's just far quicker in an exam. This helps you understand, but this is much quicker. So choose whichever way you want, either is fine. Let's have a look at problems in terms of disposal of addition polymers. The fact that they're inert means they don't react, and that therefore means they can't biodegrade, they can't degrade naturally. So what does that mean? Single-use plastics, for example, water bottles, straws, any kind of packaging or plastic bags. What's the issue with that? Well, it can take hundreds of years to degrade. You may have read recently that it's entering the food chain because it breaks into small pieces which themselves don't decompose. Fish can eat them, bigger fish eat them, we may eat the fish, and it ends up affecting us. And they've recently found small particles of plastics in humans. And potentially, plastics are a potentially poor use of crude oil, which is a very limited commodity. So that gives you a few examples of the problems with disposal of addition polymers. Burning plastics can make some sense because obviously when you burn them, they kind of disappear. But of course, that's not the case. When you burn plastics, it releases carbon dioxide into the air. And it also produces very harmful chemicals, including chemicals called dioxins, furans, heavy metals, and particulates, small particles. And those can all cause problems for organisms. So overall, when we come to the cons of plastics, durable is a problem. They last a long time. Non-biodegradable, and give off toxic fumes when burned. There's your syllabus statements. Hopefully that makes sense.